Here's a relatively tricky rigid body mechanics problem where we actually have to look at a limiting case for when a cylinder is almost escaping the confines of this cart of mass m, when the cart is being pushed by this force P, which is acting from left to right. And this is the kind of problem that you might get as a first or second year student in university doing some kind of engineering, whether it's mechanical, civil, or aerospace. And if you'd like to see anything similar to this on the channel, let me know in the comments. So the way to go about doing this is to first of all draw the free body diagram of the two objects separately. So first we'll look at the cylinder and then we'll look at the cart. So if I draw the cylinder like this, or the cross section of the cylinder, that's just going to be a circle, and this cylinder has a mass m, and the force is acting on the cylinder normally. So let's assume for now that there is no force P acting from the left. So if that's the case, we've got the weight, which is mg, and we also have a normal reaction force, which is acting upwards, and that acts to balance the cylinder vertically, because horizontally there isn't really anything going on if everything is stationary. Now, once that force P starts acting, this corner here is going to start producing a force which will be acting on the cylinder. Now, if we assume there's no friction between the cylinder and the cart, what this means is that there will be, there will be a force here acting this way, or maybe I should use a different color. So there will be a normal force acting here, and that normal force is going to be perpendicular to the circumference at that particular location for the cylinder. So there's no component of tangential force, because if there was, that means there would be friction, and there isn't. So this is the only force that will act once the system starts moving. And there will be a point when, essentially when the cylinder will start, will tend to leave the rectangular recess. What will happen is that this normal force, which is, acting between the cylinder and the base of the rectangular recess, will stop existing, and instead all of that normal force will move here. Okay, so in the limiting case, so let's write it like this. In the limiting case, what happens is that this is our cylinder, and then you have the rectangular recess, well, the corner of the rectangular recess is here, and the normal force will be acting this way. And the force will pass through the center of the cylinder, and we actually know the angle as well, because we know we know that the radius of the cylinder is r, right? So we know that the distance from here to here is r over 2. We know this distance from here to here is also r over 2. So we can actually find out what, we can actually find out the vertical and horizontal components of n. So this is theta, let's call it. So that theta is the same as this theta here. And we can find out what the value of theta is. So we can say that, for instance, sine of theta is equal to the opposite, which is r over 2, divided by the hypotenuse of that triangle, which is the radius of the cylinder. So you can cancel out the r. So this is 1 over 2, which means that theta is arc sine of 1 over 2, and arc sine of 1 over 2 is pi over 6. So that's what that angle theta is going to be. So we can then start, writing Newton's laws, or the equation of motion for the cylinder, and then we'll do the same thing for the cart. So let's draw the free body diagram for the cylinder for the third time now. So this is the cylinder. Then we have two things happening. We've got the weight, which is mg, and we also have this point here where we have a normal force that's acting straight through the center of the cylinder. So that normal force can be decomposed in a vertical and horizontal component. So we have this angle here, which is theta, which is pi over 6. So we have this force as n cosine of pi over 6, and we have this as n sine of pi over 6. Right, so Newton's laws say the following. So the sum of forces in the x direction equals the mass of the cylinder times the acceleration of the center of mass in the x direction, and then the same thing will happen in the y direction. Now, if we write what the forces are in the x direction, we only have one thing, right? So we have this n cosine of pi over 6. So that's n multiplied with cosine of 30 degrees, that's just root 3 over 2, which is m, acceleration of the center of mass in the x direction, and that's pretty much it. So let's call this equation 1. Now, for the second equation, we have that the sum of forces in the y direction equals the mass times the acceleration of the center of mass in the y direction. So in the y direction, we have two forces now. We have n sine of pi over 6, also known as n times 1 over 2, minus mg, and that's equal to the mass times the acceleration of the center of mass in the y direction. And that's the second equation. And the third equation says that essentially, that third equation refers to rotation, because this is a 2D problem. So we've got that the sum of moments, and now the question is, where do we take our moments with respect to? So let's do it with respect to C, which is the center of mass. So the sum of moments with respect to C equals the moment of inertia, which is 1 over 2 times mr squared times the angular acceleration, right? So what are the moments acting about C? Well, weight doesn't produce a moment because it's acting through the center, and n doesn't produce a moment either because it's also acting through the center. So we've got 0 equals 1/2 mr squared alpha, which means one of those has to be 0. Clearly m and r can't be 0 because those are the dimensions and the mass respectively of the cylinder, which means the only quantity that can be 0 is alpha, aka the angular acceleration. So in the limiting case, when the cylinder is just escaping the confines of that rectangular recess, there is no angular acceleration. And there's also something else that's happening, or I should say two more things that are happening. So the first thing is that the acceleration of the center of mass in the y direction, this is actually going to be equal to 0. This is equal to 0 just before the cylinder starts escaping. So essentially, if this force P becomes slightly higher than that limiting value, this stops being true. But while that P value is right on the edge of that whatever limiting value it has, which we haven't found out yet, then the acceleration of the center of mass in the y direction is equal to 0. So this quantity is equal to 0 as well, which means that we can find what the value of n is. So if we rewrite that equation 2, we have n times 1 over 2 minus mg is equal to 0, which means that n is going to equal 2mg. So with this in mind, we can then look at this, which is the first equation that's going to help us find the acceleration of the center of mass of the cylinder in the x direction. So let me write that again as n root 3 over 2 equals macm in the x direction. So n is 2mg. Then we have root 3 over 2, which is equal to m times the acceleration of the center of mass in x. We cancel out the m's. which gives us that the acceleration of the center of mass in the x direction is, we can cancel out the 2's, is g root 3, like that. Right, so then we can use this to actually say something about the acceleration of the cart. So let's draw free body diagram of the cart now. So we've got the cart here, and we've got a force that's acting this way, right? And then we also have this normal force. So this normal force acting on the cylinder in this case, it's acting from the corner of the cart on the cylinder. So which means that we have an equal and opposite force, according to Newton's third law, acting on the cart. So this is exactly the same force N, which is 2mg, but it's acting on the cart, and it's acting at the same angle, pi over 6. Right? And I'm not even going to bother with the vertical components because those are irrelevant for this problem. But we also need to consider the fact that this cart has an acceleration going horizontally to the right, called A. Now, here's the thing. While the value of P is small, so if you can imagine this value of P increasing from 0, the cart and the cylinder will move as one system, meaning they will have the same acceleration until the cylinder starts escaping. But until that point, the acceleration of the cart and the acceleration of the cylinder are going to be equal to each other. And as the cylinder still hasn't quite escaped those confines, we can still say that in this particular moment, and not a moment afterwards, but in this particular moment, the acceleration A of the cart is equal to the acceleration of the center of mass of the cylinder, which is g root 3. So that's gonna help us find what that maximum value of the force is, which just makes the cylinder start to escape. So if we rearrange this equation here, or if we write Newton's second law rather for the cart, so remember the cart has a mass capital M, we can say that P minus, and then we've got this here, which is N, and then the horizontal component is cosine of pi over 6. So minus cosine of pi over 6 equals mass times acceleration, which is g root 3. And that's it. So now we have that P minus N was, remember, 2mg. Cosine of 30 degrees is root 3 over 2. And that's equal to mg root 3. Cancel out the 2's. So we have P equals, and then we can factorize g root 3 m plus m. And that's the answer. So as long as the force, so let's write it here. So as long as P is equal to this or less than this, what it means is that the system will have the same acceleration. Right now, if P exceeds this value, then the cylinder and the cart will move in different ways, but we don't really look at that because that's the only thing the question is asking for. So that's the answer, and that's the end of the question.